Hi students, last class we discussed about the synchronous motor under load condition, and next we are on maximum, that is the characteristics of the torque angle characteristic. The characteristic curve which is drawn between the torque versus load angle, that is we call as the torque angle characteristic. Next, we are going to study about the torque in synchronous motor. Here, four different types of torque in synchronous motor. In that, the first one is starting torque. What the first one here? Starting torque. So here, the torque developed by the synchronous motor at start condition when voltage applied. That torque we call as a starting torque. It is also called as breakaway torque. It is also called as breakaway torque. It is necessary to overcome the friction and inertia. That is about the starting. And next torque is nothing but running torque. The torque which is developed by the motor under running condition, that torque we call as a running torque. It is decided, the amount, that is the magnitude of the running torque is decided by the output rating of the motor and the speed of the driven machine. The speed of the driven machine. That is about the running torque. And next one here, pull out torque. Pull out, pull in torque. Pull in torque. Pull in torque is nothing but initially the synchronous motor, that is the stator magnetic field and the rotor magnetic field, initially they are not having a synchronism. Okay. So initially synchronous motor runs with the speed less than the synchronous speed. Okay. When we run the rotor at synchronous speed with the help of the external device, that time we are switch on the excitation. Switch on the excitation. Then the rotor and the stator field both are entered into the synchronization. That is we call as synchronism. That is we call as the synchronism. That is the rotor and the stator field both are runs with the same speed. So this we call as the synchronism. At that time, here the amount of torque developed by the motor at the time of pulling into synchronism, the amount of torque developed by the motor at the time of pulling into synchronism is called pulling torque. It's called pulling torque. Fourth torque is the pull out torque. It is also called as maximum torque. It is also called as maximum torque. When the synchronous motor is loaded, that is, we operate the motor from no load to full load condition. By increasing the load gradually, here the force of magnetic attraction between the stator field and the rotor is slowly weakens. That deviation can be measured with the help of the angle delta. That is, we call as a load angle. As load increases, delta increases. When delta increases, the magnetic locking between the stator and rotor should be decreases. Okay. At theta is equal to degrees, 90 degrees, maximum load angle. At maximum load angle, the torque developed is maximum by the motor. Maximum by the motor. And the magnetic locking is weak. Magnetic locking is very weak. At delta is equal to 90 degrees, the torque developed by the motor, that torque we call as the maximum torque. That torque we call as the maximum. See that here? The maximum torque developed by the synchronous motor without pulling out of synchronism is called pull-out torque. Is called pull-out torque. Very, very important for 2 marks. Define starting torque, define running torque, define pull-in torque, define pull-out torque. Next, on the next topic, is analysis of phasor diagram. Analysis of phasor diagram. How we analyze this phasor diagram? The last topics we discussed about the magnitude of the back EMF per phase and the terminal voltage per phase, both are equal, but the direction should be opposite. This one is the back EMF and this one is the terminal voltage. Both are in which direction? Both are in opposite direction. Okay. And next one here, see that under no load condition, both are in opposite direction. But when the motor is operating under load condition. So when the motor is operating under load condition, so in that case, the back EMF is deviates from the original position by an angle delta. By an angle delta, back EMF is deviates. So that angle we call as the load angle. That angle we call as the load angle. The delta we call as the load angle. The next one, see that we note that the synchronous impedance. The expression of synchronous impedance is Zs is equal to Ra plus Jxs. Ra is the armature resistance, Xs is the synchronous reactance, and theta is equal to tan inverse of Xs by Ra. It is the internal machine angle. Internal machine angle. It is also called as impedance angle. It is also called as impedance angle. And next one here, theta is called the internal machine angle. Theta is called as internal machine angle. Is that here? Theta. What is theta? Theta is called as internal machine angle or impedance angle. Impedance angle. So the significance of internal machine angle is that it tells us that phasor, that is the current, phasor current lags behind the resultant EMF per phase. The significance of the theta, it tells that this theta decides the phasor current lags behind the ER phase, the angle between the ER phase and the IA phase, the angle between the resultant EMF per phase and the armature current per phase. That is we call as the internal machine angle. This we call as the internal machine angle. When the current, so when the type of load is inductive in nature, the current always lags. The current always lags. And next one, when the type of load is capacitive in nature, the current always leads the voltage. The current always leads the voltage. See that here the phasor diagram. In the phasor, this is the phasor diagram. Here in that phase, see that this phasor diagram. So V phase is the terminal voltage, and EB phase is the back EMF. Here the deviation of the angle. The deviation of the angle is alpha. This deviation, the deviation of the angle is alpha. See that this deviation of the angle should be alpha. It is alpha. And next one, see that the angle between the ER phase. This is the ER phase is equal to IA phase into ZS. What is the angle between these two? This is the theta. Theta is the angle. Theta is the angle. Theta is the angle between the ER phase and the IA phase. Here, three angles are there. What are those three angles? One is delta and one is theta. Okay, how many angles are there here? Three angles. So one is delta and next one is theta and next one is phi. One should be the phi. How many angles are there here? Three angles. What are those three angles? Phi, delta, and theta. Theta is the angle between the ER phase and IA phase. Delta is the angle between the EB phase and the V phase. And next one, see that here, phi is the angle between the V phase and IA phase. That is we call as the power factor. That is about this analysis of the phasor. Next coming to point, the next topic is operation of synchronous motor at constant speed. Operation of synchronous motor at constant load. Operation of synchronous motor at constant load and variable excitation. Variable excitation. The load should be the constant. Which one is variable here? Excitation should be the variable. So in the last class we discussed about the constant excitation and variable load. We drawn the excitation circuit. Here, in this concept, the synchronous motor operating at constant load. It is operating at constant load. And next one, which one is changing here? Excitation. So excitation here changing. Excitation should be variable. So when the excitation is varies, nothing but field current goes on changing. Now The performance of the synchronous motor reacts by changing its power factor of the operation. Changing its power factor of the operation. See that here, four types of excitations are. What are those four types of excitations? One is one is normal excitation, and next one is the under excitation, and next one is the over excitation, under excitation, over excitation, and next one critical excitation. How many types of excitations are there here? Four types of excitation: normal excitation, under excitation, over excitation, and critical excitation. So I will clearly explain these four topics. See that under normal excitation. Under normal excitation, here the magnitude of the back EMF is equal to the terminal voltage per phase. Terminal voltage per phase. So this condition, the excitation is the normal excitation. In normal excitation, motor draws the current is the minimum value of current. That is very less amount of current from the supply means. Okay. And next one, that power supplied from the power drags from the supply means that power we call as the input power to the motor. Input power to the motor. And next one, power factor of the motor is lagging in nature. Power factor of the motor is lagging in nature. And next one, see that what is the expression of the input power? The expression of the input power is Pn is equal to root 3 times of VL IL cos phi. For line values, for phase values, 3 times of V phase IA phase cos phi. 3 times of IA phase, EA phase cos phi. So most of the times, the voltage applied to the motor is always constant. The voltage, the supply we are given to the motor is always constant. And next one, and which one here, the term IA phase is also remains constant. So in this concept, we are going to study about the entire operation of variable excitation. Variable excitation, and the load should be constant. So the cosine component of the armature current remains constant. Cosine component of the armature current remains constant. This IA is not here, load constant, IA constant. And the cos phi, that is the cos phi is not constant, but the term IA cos phi is constant. So here cos phi here, it depends upon the excitation. Depends upon the excitation. That is the cos phi. Cos phi depends upon the type of the excitation. Either it is a normal excitation, under excitation, over excitation, okay, like that. Critical excitation. Critical excitation. See that here, four types of excitations are there. See that here, first we are going to discuss about the what type of excitation, under excitation. Under excitation, the name is under excitation. In under excitation, the magnitude of the induced EMF. Induced EMF is nothing but back EMF. In synchronous motor or motor in action, induced EMF is nothing but back EMF. So under excitation is nothing but the magnitude of the induced EMF is less than the applied voltage. That condition we call as that excitation or that kind of condition we call as the under excitation. In under excitation, the magnitude of the resultant EMF will be increases. The magnitude of the resultant EMF will be increases ER. ER is equal to IA phase ZS. When ER increases, automatically IA phase is also increases. IA phase is also increases. Here, see that when current should be increases is nothing but the type of the power factor is the lagging power factor. Which kind of power factor? Lagging power factor. So, in under excited condition, current drawn by the motor increases. Under excited condition, current drawn by the motor increases. The magnitude, the power factor cos phi decreases and becomes more and more lagging in nature. More and more lagging in nature. So in under excitation, the synchronous motor having the characteristics is the more and more lagging nature. More and more lagging nature. Next one, coming to point of next excitation is the over excitation. Over excitation. Over excitation is nothing but the magnitude of the back EMF is greater than the applied voltage. Is greater than the applied voltage. In this case also, the resultant EMF increases, and the next one, Here the angle of theta will be decreases. The angle of theta will be decreases. In overexcited condition, the synchronous motor becomes work as a leading in nature. Leading in nature. So it acts as a under overexcited synchronous motor works as a leading power factor. Means in overexcitation condition, the synchronous motor acts as a capacitor. Acts as a capacitor. Why we use the capacitor? To improve the power factor. To improve the power factor. In overexcitation, we are increasing the power factor. That is, the magnitude of the power factor increases. That is, the nature of the power factor is changes from lagging condition to the leading condition. In under excitation, magnitude of the back EMF is less than the applied voltage. In over excitation, the magnitude of the back EMF is greater than the applied voltage. So lagging nature in under excitation, leading nature in over excitation. When the synchronous motor acts as a capacitor, when if the excitation is over excitation, at over excitation condition, the synchronous motor acts as a capacitor. Acts as a capacitor. And next topic, we are discussing about the critical excitation. Critical excitation. What is critical excitation? In critical excitation, the power factor cos phi is equal to 1. Cos phi is equal to 1 means unity power factor. Unity power factor. So critical excitation, when the critical excitation is occurred, at which power factor? Unity power factor. That is the cos phi is equal to 1. When cos phi is equal to 1, here the motor drags the minimum current from the supply. Minimum current from the supply. In critical excitation, the current and the voltage both are in phase. Both are in phase. What is the power factor of resistive element? Unity power factor. Unity power factor. See that here? How many types of excitations are there? 4 types of excitation. Under excitation, over excitation, critical excitation, normal excitation. Under excitation means back EMF is less than a supply voltage. Over excitation means back EMF is greater than a supply voltage. Critical excitation means back EMF is approximately equal to applied voltage. Normal excitation means both are exactly equal. Both are exactly equal. See that here below, here, the phasor diagrams of the over excitation, under excitation. See that here. These are the phasor diagrams of the 4 excitations. Normal excitation, under excitation, over excitation. See that here in normal excitation, back EMF is approximately equal to phase. See that here. Phi is the power factor angle between the V phase and IA. Theta is the internal machine angle between the IA phase and ER phase. Delta is the angle between the V phase and IR axis of the V phase and EB phase. And next one, see that here. Observe under excitation, it acts as a lagging nature. That is power factor, lagging power factor. What about IA? IA should be increases. See that here. Here phi is more when compared with the normal excitation. In over excitation, back EMF is greater than the terminal voltage per phase. Type of power factor is the leading power factor. Here also the armature current increases. But see the waveform. It is the current phasor rotates in which direction? Anti-clockwise direction. What is the angle between this E phase and IA? Phi. The angle between ER and IA is the theta. And the last one, last excitation is the critical excitation. Critical excitation is nothing but both are in phase with each other. What are both are in phase? Current and voltage. Okay. And next one, EB phase is approximately equal to V phase. At which power factor? Unity power factor. This phi is equal to 0. IA should be 0. So these are the concepts related to the synchronous motor. The concepts we are discussed here in this class. Types of torques in synchronous motor. 4 types of torques are there in the synchronous motor. An analysis of this diagram. Next, we study the under excitation, different types of excitation. Here, load should be constant, but this one is varying here excitation. should be. So depends upon the excitation, the different characteristics of the synchronous motor: under excitation, over excitation, normal excitation, critical excitation. Okay, students, you have to go through the material. Thanks to all.